Hold on, yeah. Okay, so last week we have discussed about PN junction under thermal equilibrium, right? So we've discussed that um upon the formation of PN junction, we're going to see diffusion and drift of all carriers. So diffusion takes place when there is a concentration gradient at a junction. For example, if we're talking about P-type silicon on the left on this slide, the blue one, blue region, okay? So we're going to have a diffusion of holes from the blue region into the red region because of the presence of the diffusion concentration gradient, right? So we have high concentration in the P-type region for holes and low concentration for holes in the N-type region. So therefore, we're going to have a diffusion. At the same time, we're going to have drift component as well of hole, where the minority carrier hole, carrier which is hole, in the N-type on the right-hand side in the red region is going to be withdrawn. It's going to be akan ditarik oleh electric field near the junction from the N-type into P-type, right? So hole is the minority in N-type, majority is electron. So these minority holes are going to be withdrawn by or swept. Macam dia kena sapu, ditarik, dan ditarik macam tarik, baling ke belah sana. Then swept into P-type region where the holes are going to become majority carriers because we have holes as the majority carriers in the P-type, right, the blue region. So as a result of this transport mechanism, we're going to have current density associated with both, right? Diffusion of hole and drift of hole. And these can be written as J diffusion and J drift, right? J diffusion is given by negative QD dPdx based on what we learned before in carrier transport phenomena. And we're also going to have a J drift component due to hole, which is given by conductivity times electric field, where conductivity is given by the QP mu H, right? So note the directions of both drift and diffusion components. So diffusion component is from the left-hand side to the right-hand side for holes, P-type to N-type, and you're going to have at the same time drift component on the opposite side from N-type to P-type, right? So we're going to have two opposing directions of current density at the same time. So the same is also applicable to electrons. So due to the concentration gradient of electrons from N-type to P-type, from the red region to the blue region, we're going to see diffusion of electrons from the right-hand side in the red region to the blue region, right? Where the concentration of the electrons is high in N-type and low in the P-type. So at the same time, we're also going to have drift component of minority carrier electrons in the P-type material in the blue region to the red region where they are swept by the electric field at the junction. Just exactly what happened to the hole like we discussed on the previous page. So as a result, we're going to have true current density as well. So the first one belongs to drift of electron, which is moving from left to right, P-type to N-type, and you're going to get sigma E as well, right? Conductivity times E, Q, N, mu E times E, and diffusion component due to electrons from N-type to P-type region, and this is going to be given by QD dx, right? So note the directions and also the carrier concentration profile from left-hand side to right-hand side, right? So for this particular case, you can see the NP is low in the P-type region, and then at the junction is going up, and it's going to be very high in the N-type region. The same is also applicable in the previous page, right? So we have holes as the majority, so that's why it's high in the P-type, and then it goes down almost abruptly at the junction, and then it goes to low concentration in the N-type because holes now become minority carriers in N-type. So this is fine. So this is another summary that we can see for p-n junction. So the p side, the p type is on the left hand side, the n type is on the right hand side. So we have discussed last week that we're going to have a fixed space charge regions near the p-n junction right in the middle, right? Or we also call this central region as depletion region. Depletion region or space charge region, right? So last week we've also discussed that all the regions to the left of the space charge is neutral in nature, and also applicable to the right. Right? This neutral region to the left and to the right will be called quasi-neutral region. We're gonna talk about this a little bit later. We call it quasi-neutral region, right? Quasi-neutral, quasi-neutral, quasi-neutral. RS4 region, yeah. So yep, so you're gonna have electric field near the junction, and we've seen diffusion of holes from left to right. We've also seen diffusion of electrons from right to left, and on the other hand, we've seen drift component of both carriers as well in the opposite direction to the diffusion components. Okay, two isolated pieces of P and N semiconductor at thermal equilibrium have different Fermi levels. So in the previous topic, the last two topics or three topics, we've discussed about the Fermi level of p-type and n-type, and we have learned that the Fermi level of n-type semiconductor is near to the conduction band H. Okay, and we've also learned that the Fermi level of the p-type is near to the valence band H. Okay, so we can label them as EF and EF in N or EF in P, right? So therefore we call them as EFN and EFP, right? So what you see up here, you can also see down there. So it follows, yeah, follows. So the p-type material is on the left-hand side, the right-hand side is on n-type material. And for the p-type material, we call the majority carriers as PP naught, right? Remember the three things, PP naught. So density of holes in p-type material at thermal equilibrium, and that is given by Na because we assume 100% ionization. So since we know the majority carriers in the p-type material, therefore we can calculate the minority carriers in the p-type material, and this is given by Np naught, right? So remember the majority carriers are holes, and therefore the minority carriers are electrons. So the minority carriers in the p-type is given by Np naught. Density of electrons in p-type material at thermal equilibrium, which is given by law of mass action, and you can write it as Ni squared over Na, right? Ni squared over Na or Ni squared over Pp naught, right? Same thing. Right, the same thing can also be seen in n-type material where the majority carriers are electrons, and they are labeled as N and naught, right? Density of electrons in n-type material at thermal equilibrium, and it is equal to Nd because we assume 100% ionization as well. And therefore, using law of mass action, you can calculate minority carriers in n-type material, which is holes, right? P and naught. Density of holes in n-type material at thermal equilibrium, and is going to be given by N squared over Nd or N squared over N and naught, right? Same thing. And we have learned that the Fermi levels are different for each p-type and n-type. The levels are different, right? So the actual position of EF depends on the concentration of dopant atoms in each of the semiconductor material. So we have learned that intrinsic has EF right in the middle of the band gap. Then as you increase the doping level, say for n-type, you're going to have your EF increases going closer and closer and closer to the conduction band edge. On the other hand, if you dope your material p-type, your EF from intrinsic is going to move from the mid gap, right, central of the band gap, lower and lower and lower, closer to the valence band edge, right?
two isolated pieces of semiconductor material at room temperature, the thermal equilibrium, free carrier density, and the Fermi levels is given by the illustrated diagrams. So once we connected the two pieces together, the P and N together, and let thermal equilibrium establish itself, which means no light, no voltage, no temperature differences acting on the P-N junction. Remember last time we learned about thermal equilibrium, right? Nothing is acting on the system, right? So whereas for steady state, something is acting on the system, but it's constant with time, right? So in this case, we're talking about thermal equilibrium, TE. So then the two Fermi levels align because of a system at thermal equilibrium only has one Fermi level, right? If you talk about a system at thermal equilibrium, we are only going to have one single EF, right? So we used to have P, Fermi level for P closer to the valence band age, and for N closer to conduction band age. But upon combination of P and N, we only going to have one Fermi level, right? The Fermi level of both sides are going to align and only form one at thermal equilibrium. The alignment occurs very quickly via a carrier distribution, right? Away from the junction, the bulk conditions dominate, right? We've discussed this now. When you go away from the depletion region, for example, the bulk condition dominates. That means the neutral condition. So we're only talking about this region, right? P and N together. So now let's look at the band diagrams upon combination of P and junction. So the EF aligns. If you look at this, if you look at the left-hand side, you can still, well, you can separate this like this first. Okay, boleh tengok P-type on the left, N-type on the right, 1 and 2. You can see Fermi level of the P-type is still staying near the valence band age, and Fermi level for the N-type is still staying at the conduction band age, but the band actually adjusts themselves, or you're going to have some bending in the middle in order to align the Fermi level, right? So we're going to end up with a single Fermi level, and we're going to have a barrier height form Q psi, not barrier height form at the junction, which stops the transport of the carriers to the neighboring region, right? Upon connection of the two pieces, the carrier redistribution occurs until a constant electrochemical potential, that is the Fermi level, is established. So you only have one by the thermal equilibrium time. And energy barrier results at the junction. So this energy barrier is what stops the further diffusion of the holes into N-type and further diffusion of electrons into P-type. So at this point, you're going to have electrons staying in N-type and holes staying in the P-type, okay, due to the formation of energy barrier. So macam ada tembok lah, macam ada some barrier for the carriers to further diffuse. So that makes them cannot diffuse anymore. So if you want to put this on the band diagram, right? So you can draw this band diagram, and then you can still represent the movement of carriers by drift and by diffusion. So electrons is red and holes blue. Okay. So you can see here P side is on the left hand side, N side is on the right hand side, and upon thermal equilibrium, so this is already at thermal equilibrium, we are only left with a single Fermi level, right? And we have bending in the middle. So we need bending. This is what we call bending. So, right, in order to accommodate a single Fermi level, and we can see the directions of both diffusions and drift of both carriers, right? So diffusion of electrons, for example, taking place from N-type to P-type, then drift of electrons taking place from P-type to N-type, and the exact opposite is happening for the holes. Diffusion of holes from P-type to N-type, drift of holes from N-type to P-type. Okay,
And this central region is the depletion region from this minus xp to xn, right? This is the whole thing. So depletion region, or you can also say space charge region, SCR, space charge region. Okay. So you should be able to sketch this up, right? The energy band diagram, the carrier transport directions, the EC, the EF, the EI, the EV, the depletion region, dimension, right? Label the electrons, the holes, and eventually the barrier height. Okay, the barrier height. Once thermal equilibrium is established, right? Don't forget to label the energy axis and the distance as well, right? On the y and x axis. Okay, you have to go back and try yourself. Try to draw this without looking at the example. Then you can tell whether you understand or not. So at the interface, a potential change or energy barrier, potential change or the energy barrier occurs. Right, the built-in potential is calculated as follows. So we at thermal equilibrium, you can calculate the built-in potential VBI, which is equal to psi naught at thermal equilibrium, and equals to VT. VT is thermal voltage times ln NA times ND over NS squared, right? So it originates from the above derivation, okay? So it can be summarized as a VT ln NA ND NS squared. So the thermal voltage is known, right? So you can calculate the thermal voltage based on the given temperature. Then NA is the acceptor level for p-type, ND is the donor level for n-type, and NS squared is already known for any material given. For example, if we talk about silicon, then we're talking about 1 times 10 to the 10. So from here, you can already calculate your built-in potential at thermal equilibrium. So it also can be written as, you can see the next slide later on, VT ln PP naught over PN naught also equals to VT ln NN naught over NP naught, right? Density of, this is the majority carrier in P-type, majority carrier holes in P-type, and minority carrier holes in N-type, and majority carrier electrons in N-type, minority carrier electrons in P-type. Okay. So you can use this equation. So it can be rearranged as the following, equation 1 and 2. So from the above equation, you can rearrange this into these two equations. So if you look at this equation 1 and 2, you can use these equations to calculate minority carrier concentration. Okay, equation 1 is for minority carrier hole in N-type at thermal equilibrium, and that is equal to PP naught. That is the majority carrier hole at thermal equilibrium, exponential of a negative Q VBI over KT, and the same is also applicable to minority carrier electrons. Right? Why this is important? Let's see the below diagram. So if you look at this diagram, so y-axis is for the ln of electrons or ln for holes, and x-axis is for the distance across the p-n junction. So p-type is on the left hand side, n-type is on the right hand side, and this central region is the depletion region or SCR, space charge region. Okay, so as we discussed before, we can see here, or we can represent in the other way, that in p-type, pp naught is equal to Na, and minority carrier electrons is given by MP naught, which is equal to Ni squared over Na. On the other hand, in N-type material, the majority is electron and is given by Nn naught equals to Nd, Therefore, the minority is given by Pn naught, minority carrier holes in n-type, equals to ns squared over nd, right? So we're going to do some calculation on this later on. All right, so carrier densities in a p-n junction diode at thermal equilibrium at room temperature. So note the shape of the curve and the profile first. Hold on, yeah, okay. From this equation, from this plot, you can plot space charge density, the SCR, and that is given by this equation, Q times P minus N plus ND minus NA. The result at room temperature is shown below. So if you look at the depletion region alone, so you can see that this is the whole SCR. Okay, this is the whole SCR. So I can plot here on the y-axis is the space charge density, right? So this is the space charge density on the y-axis given by Q and D and negative Q and A, and x-axis is the distance across the p-n junction, and this central region is the SCR where you only have your charges here. So we don't have any charges on to the left and to the right. So that's why if you want to relate this to the previous illustration, we are talking about this region now. We're talking about this region where you have all the charges, but there's no charges to the left, no charges to the right. Okay, so we plot this as a graph like this, right? So this shows the distribution of the charges in the depletion region or the space charge, where the positive charge region, which is a little bit smeared, has an equal area to the positive or negative charge region on the other side. Okay, but the areas of both are equal to each other, right? Q and D and Q and A. So if you want to relate to the p-n junction that we discussed just now, kalau you nak draw a block diagram again, so the left hand side will be the P, the right hand side will be the N. So that's why you see the right hand side is positively charged because it's originated from the N semiconductor, and that's given, the magnitude is given by Q and D here on the y-axis. And on the other hand, if you look at the negative side of the charges, so it originated from the p-type material, so therefore the SCR in the center is negative because it's the opposite kind, is of opposite nature, and the magnitude is given by Q and A, right? So that's how you can plot the space charge density on the y-axis. Space charge density across the abrupt p-n junction at room temperature is given above. The two humps, right? The two humps, this one and that one, are due to the immobilized ionized dopant atoms. Remember last time we talked about the mobile charges, which are electrons and holes that are diffusing across, and as a result of the diffusion of both electrons and hole, we're gonna be left with immobile ionized charges in the SCR. Immobile. So these are fixed charges. They are not moving. Okay, fixed charges. For electron, for the negative side is going to be positive. For the whole side is going to be negative. Right? This is immobile, not moving. The first one is mobile. So a large electric field is associated with these two humps, right? Due to the presence of the charges, we're going to have electric field across the junction that will be responsible for the drift component of the carriers, electrons and holes. Right, the same thing. If you want to plot this, a depletion approximation in the space charge region SCR, the carrier density in N and P are assumed to be negligible compared to NA and ND. Right, the carrier densities are assumed to be negligible. Why? Because these regions have lost their electrons and holes due to diffusion that was happening before thermal equilibrium. So that's why the carrier densities in the SCR are low, so much lower in comparison to the NA and ND on the left hand side and on the right hand side of the PN junction central region. Okay, so that's why we say that it's negligible, because the carriers are lost due to diffusion before thermal equilibrium is established. Outside the depletion region, the space charge is 0, right? Outside the depletion region, the space charge is 0. So if you talk about this first plot, so the magnitude of the charge outside the depletion region is 0. Here, there's 0. And that one is also 0. But if you talk about within the depletion region, so this is depletion region or the SCR. So write down SCR, which is also depletion region, DR lah, tak DR. So you can see positive charges on the N side and negative charges on the P side. Right? Same thing like what we saw on the previous page. And as a result, so dE dx is going to be given by this. The electric field at the junction is going to take this shape, right? Take this shape due to dP dx. Right? So space charge density, electric field. The second one is electric field. So this one is space charge density, and this one is electric field across PN junction, right? So if you got this dE dx, but if you want to see the magnitude of the built-in potential, it's going to look something like this at a junction. So it's going to have a build-up across a junction. So it's going to have a build-up across the junction that will stop further diffusion of carriers across the junction. So once the thermal equilibrium is established, if you recall before this, we used to have diffusion of electrons from N-type to P-type, diffusion of holes from P-type to N-type, and we're going to have a drift of electrons from P-type to N-type and drift of holes from N-type to P-type, right? So due to the presence of a very high and built-in potential, this will stop further movement of the holes and electrons to the opposite side. Okay, so at thermal equilibrium, we're not going to have any diffusion, any movement at all, right? Any movement at all. So you can also see this on, you can come to the PV CD-ROM. Let me show you. Thermal equilibrium. Okay, let me share. Thermal equilibrium. Okay, can you see the website? PV CD-ROM? Okay, good. Right, you can come to PN junction diodes. You can come here, formation of PN junction, and you can come here to PN junction diode 3.5. Then you can see this. What happens in thermal equilibrium? Net current from the device is 0. Electron drift current and electron diffusion current exactly balance out, right? Similarly, the hole drift and hole diffusion also balance out each other. So let's see. So 0 voltage across diode, there's no net current flow, right? We have electric field across the junction. We have on the P side, on the left hand side, we're going to have a negative fixed charge. Okay, tadi kita plot Q and A, right? Negative Q and A. So this is it. This is the Q and A thing. And on the right hand side here, I'm pointing to the right hand side. In the space charge region of the N side, you're going to have the magnitude of Q and D, right? Q and D, right? Remember the satu yang ke atas, satu yang ke bawah tu, both two humps. So it's actually belong to these two regions, right? So the neutral region that we are referring to, that we referred to before, was the left hand side of this, further left and further right. Okay, ini untuk simplicity je, kita tengok kat central region je. But if you want to put everything together, then you have to put the bulk as well, the bulk component of the p-type and n-type, before you can actually connect the electrodes. This one, the gray ones, are the electrodes. So you can see electron diffusion from right to left. You can see electron drift from left to right. You can also see hole diffusion from left to right. You can also see hole drift from left to right, right to left, sorry. Okay, so this is the thing that we discuss as our J diffusion for hole, J drift hole, J diffusion electron, and J drift electrons. So next, tomorrow we're going to see what's going to happen to the thermal equilibrium condition. So the moment we introduce some bias. Sekarang kita dah capai thermal equilibrium. Okay, so it's already settled, if you like. Now what's going to happen if we disturb the junction, right? Sekarang kita dah tahu kata once thermal equilibrium is established, we are not going to have any movement of the carriers already. Right? But however, when we introduce some external agents like bias or illumination, which we're going to cover next, we're going to see some changes happening to the PN junction. So you can try this out. The VBI calculation, we discussed about the VT ln NA ND over NR squared. It's very straightforward here. You can see the temperature is given, NA is given, ND is given. NI, you can use 1.5, 1.0, then you can get your VBI, the built-in potential, accordingly from the calculation. And then space charge width, we can also quantify the width of the space charge in the center here, right? So to do that, you can calculate the xn and also xp, right? So the space charge on the left hand side, on the p side. So we need to use these parameters, VBI, NAND, and all the stuff, right? So it is the distance that space charge region extends to the p-type n-type. So it's just the central region, but the dimension of both regions, right? Or also called depletion region width. So if you plus xn and xp, you're going to have the whole stretch of the depletion region, and given by W. So W is xn plus xp, n side plus p side, and you can also calculate W on its own without going through this xn and xp thing. You can just plug in all the given values into this equation to be able to come out with the dimension of the W here. Okay. So you can go through this calculation. For example, T at 300K, NA is given, ND is given. Then you can use the calculation to calculate, right? So everything else given here. Permittivity, you need to calculate the permittivity first using the relative value of permittivity, right? Then Q is known, NA and D is known, and the W for this case is about 0.9 micron, 0.95 micron. So there's a whole stretch of your whole depletion region. Okay, so we're done with PN junction at thermal equilibrium. So is it okay so far? So we're going to move on to PN junction under bias conditions tomorrow. And Wednesday is going to be on test 1. So tak ada class. Saya akan upload, and then you can just proceed during class time. And Wednesday, the last day, we're going to have a PN junction under illumination, right? And then you are off for your mid-sem break. Then upon coming back, we're going to continue with PN junction, metal, semiconductor junction, and we're going to move into PN junction devices. So is it okay so far? All good? Right, so remember your test 1 is going to cover until this point, right? From introduction until PN junction under thermal equilibrium. Okay then, if there's nothing, then I'll see you tomorrow, inshallah. Bye-bye, take care, assalamualaikum.